by the structure of the disks. So what you actually see here is a near-infrared image, not a sub-millimeter image of a young disk, and you see the midplane and also scattering lobes, but you don't see the central star. Most of the mass is actually in molecular hydrogen, not in one of the organic molecules. And the next abundant molecule is CO, and the abundance compared to hydrogen is only 10 to minus 5 or 10 to minus 6. So this gives you an idea how sensitive you have to be to observe some of the molecules. We also know that these disks contain some complex molecules like polyaromatic hydrocarbons, which you can actually trace back by infrared spectroscopy. And then 1% of the mass is in small dust particles. Small means micron size to millimeter sizes, and the composition is mostly silicates, amorphous or crystalline, or carbonaceous solids. Actually, disks come in a wide range of masses and sizes. They have atmospheres, inner rims, gaps, spirals, and Catherine already talked about the chemical diversity, but they also have a physical diversity. And that is also needed if we want to explain the diversity of exoplanets. In addition, there are a special class of accretion disks which transport angular momentum and mass. And that means the disk environment is actually a very dynamic environment for the chemistry. So here you see some of the structures in a cartoon picture. On the left side, you see the indication of dust settling to the midplane and the radial transport, but you also have turbulent mixing, you have grain growth, and finally you may have a giant planet which blocks the transport. On the right side, you actually see the different layers of chemistry. The surface layer is mostly a layer which is dominated by UV photons. Then you have a molecular layer, and we already talked about the molecular ices, which are sitting at the midplane in the very areas of the disk. So what you should take from here is that you have huge range in temperature and density, that the chemistry is actually coupled to your dust properties, to the irradiation by the central star, and the dynamics in these disks. Just to give you an idea what I mean with dynamics, this is actually an MHD simulation of a disk, which shows you the velocity structure as a function of sound speed and the function of the pressure scale heights. And you get a bit of an idea how much mixing would go on for your chemistry. In addition, we actually have a very good idea how long-lived our gas-rich disks are. What I show you here is a disk frequency as a function of age, either measured by dust continuum observations, mostly with Spitzer at that time, or gas observations. And in both cases, we get a median age of about 3 megayears. If you consider planet formation, that is actually a very small time scale. And if you compare that with models for terrestrial planet formation, which assume much longer time scales, we have to be very fast. So Catherine already showed you the diversity in chemistry, but here's a diversity in structures. There is nothing like a smooth disk any longer. So we teach our students for a long time that we have power laws for temperatures and surface densities. Now we see all these ring structures, but we also see spirals in certain classes of massive disks. So that has to be taken into account if you want to understand the chemistry. Just to give you one idea what we can do with chemistry, I show you a comparison of the dust continuum emission in the upper panel, and then you see the CO emission and the N2H plus emission. And you see that N2H plus is actually anti-correlated with CO. And the reason for that is that N2H plus reacts with CO and forms HCO plus. So in other words, you can use N2H plus as a tracer for the snow line of CO. N2H plus is abundant, whereas CO is frozen out. You can also do 2D modeling, which changes the picture a little bit, but gives you an idea what you actually can do with CO and N2H. Then there is another coupling, which I already mentioned, that is a coupling between mixing and chemistry. And here again, you see the radial direction, the x-axis, and the scale height. And the y-axis, somebody has his micro on, so I would appreciate if it switched off. So you see the stationary model, and you see that in the midplane, and that's the calculation for gas phase CO, all the CO is actually frozen out. And if you add vertical or radial mixing, and then at the end 2D mixing, you see that you can actually explain why we see the very cold CO instead, despite the fact that CO should actually be frozen out. So mixing obviously is changing the picture quite a lot. We talked about chemistry, but I think I should remind you that we have two types of chemistry: a gas phase chemistry, which is at the surface at least triggered by ions. So you ionize H2 and you transfer the proton to another H2 and you get H3 plus, and triggers a molecule-ion reaction chain. But we learned in the recent years that even neutral-neutral reactions may operate at low temperatures. And the other possibility is that you have surface reactions, either radical chemistry, a chemistry triggered by excited atomic oxygen atoms, or you also have reactions where you start with CO, add a hydrogen atom, and this way you can actually build up methanol. So the early days of spectroscopy at submillimeter wavelengths with interferometers started about 20 years ago. And at that time, we already have seen molecules like HCO plus, CN, HCN, and DCO plus. But the real revolution, and that was also pointed out by Catherine already, came with ALMA, where we saw a number of other molecules. However, I wanted to point your attention to the fact that most of these molecules are composed of carbon, hydrogen, nitrogen, maybe sulfur, but oxygen-bearing species are actually relatively rare. Methanol was detected in TW Hydra by Catherine and company, and recently it was detected in another source, but this is a warm object, and actually, in this case, we could also assume external delivery. So there's obviously an issue that we do not see oxygen-rich molecules in most of these, despite very sensitive searches. And for methanol, the abundance is really very low. So what's the reason for that we don't see that? I will come back to that in a second. What you see here is the surface chemistry product, that is formic acid observed in tetrahydra again. So you see actually products of surface chemistry. And because there was a question by Paul, can you actually also see the ices? There is actually one way where we can do an experiment, or better, nature is doing experiment. There are sources which have outbursts, and these outbursts, in a way, change the sublimation front. And this has been done in the specific source V883 Ori, and Fantov et al. Found then methanol, acetaldehyde, and acetone popping up. So this is somehow a direct connection to what should exist on the surface of these grains. But indeed, JWST should be in the position to measure the ice composition, both in etchant discs and in discs where we have background sources. In general, if you just plot, and that doesn't have changed since this plot, if you plot the abundances in molecular clouds and compare this with abundances in discs, you will find out that the abundances in discs are all much lower. So there is some depletion going on in your discs, and again, that indicates that you have a gas-grain interaction. For CO, it's even more the case, especially in the outer discs. We actually have a strong underabundance of CO compared to the molecular cloud abundance. We also do not see cold water in the far infrared. That was actually a main result from the Herschel Observatory. We only see warm water or hot water with Spitzer at the shorter wavelengths, but not at the longer wavelengths, which again indicates that most of the water is certainly sitting in the midplane on cranes. Before I discuss a little bit more the chemistry results, I wanted to show you what we are normally doing when we model the chemistry in these disks, and that is a model for C2H, but also for higher carbon atoms. And the important thing is that you realize if you add oxygen to such a network, that really serves as a poison because then you go back to CO or simple oxygen-containing molecules, and you stop the production pathway to complex molecules. So one of the interesting discoveries, and something quite unexpected, was a finding that disks are actually surrounded by hydrocarbon rings. And these hydrocarbon rings need somehow two conditions. One is that you have a relatively high UV field so that you get atomic carbon from carbon monoxide, and then the carbon monoxide can react with, that the carbon can react with H3+, and then recombine to C2H, for instance. The other condition is that the carbon to oxygen ratio is larger than 1. So in other words, you must remove more volatiles from the molecular formation zone. So there must be more water being removed than CO. Otherwise, you would not get these high ratios. Just to remind you, of course, solar abundances are oxygen rich, and in most of the planetary atmospheres, we actually see a ratio which is smaller than 1. So we do not see carbon-rich atmospheres in giant planets, which actually points to the fact that the material the giant planets obtain, especially also in their atmospheres, is not coming from the gas phase necessarily, but pebble accretion may actually play a big role in the enrichment process, both in terms of general metallicity, but also in terms of C2 ratio. So all this indicates that you have oxygen sequestration toward the midplane of the disk, and that certainly can explain the molecular rings. Here's another molecular ring we observed, and again, TW hydrate. Here you see also the CN structure. Let me move in wavelengths, and that will be my final slides. If you go to the infrared and do infrared spectroscopy, you now trace the inner disk, no longer the disk at many astronomical units. It's more in the terrestrial planet forming zone. And you also trace mostly the midplane. And what we have seen, apart from ions and neutrals, we have seen water, dissociation product of water, OH. We have seen CO2, HCN, and C2H2. And this is exactly the wavelength range where in the mid-infrared, where JWST will provide us enormous amount of new information in the coming years. And just to tell you about the diversity we already see with the Spitzer data, on the left side, you see a comparison of HCN C2H2 for two types of stars, for a sun-like star and a cool star. And you immediately realize that HCN is not present in the cool star disks, and probably because we cannot dissociate molecular nitrogen in these disks. And on the right side, you see amazing spectrum of water. There's not noise. All these little bands you see are real. So these are all bands of water. And we see quite a diversity already in the inner disk atmosphere chemistry. But with Spitzer, we just scratched the surface. And I think we will see much more of these results in the coming years. And finally, let me just show you a spectrum, again, obtained with Spitzer, infrared spectrum on the left side of a number of objects with disks. And you see here that all these disks show very strong infrared features, and they are interpreted as different classes of pHs, and the strong UV field certainly shape these molecules quite a lot. So I think we have seen a rapid dust and gas evolution in these disks. We have also now strong indications for a rich molecular chemistry in planet-forming disks. I should actually change this to diverse molecular chemistry. We see a diversity and abundances of organic species of water. And I showed you at least 2 examples how chemistry can be used to trace the physical structure of these disks. Thank you.
Thank you very much, Thomas.